In this video, we will use superposition theorem to solve numerical problems. And the circuits we will be using will have three cases. First one will be circuit with two voltage sources. So we will have a circuit where we will have two voltage sources and we will solve the circuit for current and voltage values. The second numerical problem will be about circuit with one voltage source and one current source. And the last one will be with the circuit having two current sources. So let's go and solve the numerical problems. Before that, we will introduce some basic concept of the superposition theorem. Just a brief introduction. The superposition theorem is actually a theorem used for solving the circuit with multiple independent sources. So what we do is that we solve the circuit with independent sources by assuming that only one source is contributing to the circuit while we short circuit or open circuit the other sources. So if we have voltage source and then we use a short circuit for that, and if we have current source, we use an open circuit for that, right? So we simply replace the voltage source with open circuit right here and the voltage source with the short circuit. This is only used in superposition theorem when we have multiple sources. So what we will do is that firstly we will assume one voltage source and solve the circuit, then assume the second source and solve the circuit. So this will be much more easily explained in the numerical problems in the next slide. So let's solve the numerical problem and understand the superposition theorem. So let's start with the first numerical problem in which we have two voltage sources. So we can see we have first voltage source over here and then a second voltage source over here. Let's say the value of these voltages are 12 volts and this is second voltage is 6 volts. Similarly, let us assume first resistance is 4 ohm, second resistance is 6 ohm, and the third one, which is actually the load resistance, this is 12 ohm. So first of all, we will do is the first case. In first case, we only assume that the first voltage is active and the second one is inactive. So when the second one will be inactive, so we have to see if it is a voltage source or a current source. So if it is a voltage source, we can clearly see over here. So voltage sources are actually short circuited. Remember this, okay? Short circuit. So this diagram will actually look like this once we begin with the superposition theorem. This will stay same as this because we don't change anything with the resistances. We only change the sources. So since this is a voltage source, so this will be short circuited and we will have a circuit like this. Now we have V1 equal to 12 volt and all the other values remain the same. So what we will do is that we will apply Kirchhoff's voltage law in both loops and try to determine the values of I1 and I2 and then determine the current through this load resistance. So the first step is that we have to define the flow of current. So we have to do this in the beginning and be consistent throughout the solution. So let's say this is the first loop and this is the flow of first current. And this is the second loop and this is the flow of current. Now we will apply the Kirchhoff's voltage law in the first loop. This is the first loop. So according to Kirchhoff's voltage law, we know that sum of all the voltages in the loop is 0. So when we apply Kirchhoff's voltage law, this will become minus V1 plus voltage across this resistance, this one, this is R1, right? So voltage across R1 plus voltage across R3, which is this one, right? So voltage across R3, and then there is nothing else left, so this equals to 0. Summation of all the voltages is equal to 0. Now simply I will replace these voltages using Ohm's law. So we know that Ohm's law says that V is equal to IR. This is important. So, and substitute the values. So V1 is equal to 12. So this will become minus 12 plus. Now VR1, this will become I1 because in the first loop the current is I1 and then times resistance. So resistance is R1 plus. Now voltage across R3. Now this is a key concept over here. This resistance, if you look over here, let me highlight it with the other color. If you look at this R3, this is actually shared between both the loops, right? So for this, the Ohm law will vary. The Ohm law will actually become V is equal to I1 minus I2 times R, because the current flow through this is I1 and I2. Now, the reason for this subtraction is that if we apply Kirchhoff's current law at this node, so we can clearly see I1 is entering from the top in this resistance and I2 is entering from the bottom. So since they are in opposite direction, then we will have a subtraction over here. So don't make mistake with this. Another key point is that when we are solving the first loop, let's say this is the first loop, when we are solving the first loop, so we must write I1 first. We will see later on when we will solve the second loop, then this Ohm law will be written as I2 minus I1 times R. Okay, remember this. This is a very key concept in using superposition theorem. So since we are dealing with the first loop, so I will write here this as I1 minus I2 times R equal to 0. Now this R is actually R3, so don't make mistake with this as well. Okay, now I have this Kirchhoff's voltage law, and I know the value of R1 and R3. I will simply substitute these values. So let's substitute the values of these resistances. So this becomes minus 12 plus. Now R1 is 4, so this becomes 4I1 plus I1 minus I2. What is the value of R3? R3, which is actually load resistance, this is 12. This becomes equal to 0. So this becomes minus 12 plus 4I1 plus 12I1 minus, 12I2 equal to 0. So now I have to simplify this. This becomes 16I1 minus 12I2 equal to, I will move this 12 to the right hand side. So after moving 12 on the right hand side, this becomes my first equation, because I cannot solve it any further. So I will call this as the first equation because I have two unknowns and one equation. In order to solve this, what I will do is that I will apply the KVL in the second loop, keeping the same case A, which is only V1 is active. So let's apply KVL in the second loop, proceed with the solution in the next slide. In this second loop, while this is short-circuited, so I will use this notation for short-circuited, and this is 4 ohm, this is 6, this is 12, and the input voltage is 12 volts. So the KVL in the second loop, this one, so this will become KVL in the second loop will become VR3, right, plus VR2, and this V2, this does not exist. So, okay, even if I want to write it, that's okay. Later on, I will substitute this as 0 because we are assuming that the second source is short-circuited. So whenever the second source is short-circuited, its voltage drop is 0. The reason behind that is we know that from Ohm law, V is equal to IR. For short-circuit resistance is 0 ohm. So when this resistance is 0, voltage will automatically become 0 ohm. So this V2 in the first case where V1 is active will be 0. So I can either do it directly or I can also write V2 as 0, but let's do it directly because we are assuming this is short-circuited, right? So this becomes VR3 plus VR2 equal to 0. Now, voltage across third resistance. Once again, take notes of this. This R3 is actually shared between both loops. So the Ohm law will actually become I1 minus I2 or I2 minus I1. So remember that since we are applying the KVL in the second loop, so this time this will become I2 minus I1. This is a standard method, okay? When you are solving a KVL in a particular loop, so that current will be written first and then minus the second one. Now, what is the voltage across R2? This will stay as it is because this is not shared with other circuits. So this will be I2 flowing across R2 equal to 0. Now I simply will substitute the values of R3 and R2. So this will become, sorry, this is a mistake. This is 1, okay? Remember, this is 1, I2 minus I1. So I2 minus I1 times R3 plus I2, R2 equal to 0. This becomes I2 minus I1 times R3 is 12 plus I2 times R2 is 6. This is equal to 0. This becomes 12 I2 minus 12 I1 plus 6. Let me rewrite it. Let me rewrite it clearly. This becomes 6 I2 equal to 0. So this becomes 18 I2 minus 12 I1 equal to 0. Or I can write it 12 I1 to be consistent with the variable definition, because previously we had I1 written first. So I just want to be consistent with that. So minus 12 I1 plus 18 I2 equal to 0. So this is my second equation. Okay. So this second equation is actually for the first case. Remember that this is for the first case where only V1 is active. So we will do the same process, but short circuit the first voltage and keep the second voltage as an active source. But before that, what we have to do is that we have to solve the equations which we got and obtain the value of I1 and I2, and then we will calculate the current across this R3. So let's do that in the next slide. First case, the first equation, which I applied KVL in the first loop, and then the second equation is for the KVL applied in the second loop. But remember that this is for the first case when only V1 was active. So the equations were, let me rewrite it over here, 16 I1 minus 12 I2 plus, sorry, this was equal to 12, right? This was equal to 12. So the second equation was minus 12 I1 plus 18 I2 is equal to 0, right? So now we simply have to solve this equation because we have two equations and two unknown. So we can find the value of I1 and I2. So we can solve this using calculators, MATLAB, or we can also use some mathematics to solve this equation, which is really easy. So what we can do is that from equation 2, I always recommend using an equation which has 0 on the right-hand side to do this process. You will see now. From equation number 2, what we can do is that we can write minus 12 I1 is equal to minus 18 I2. Minus cancels out, and I1 becomes 18 by 12 I2, right? Or I can further simplify it. I1 becomes, I can divide this both with 6. So this becomes 3 by 2 I2. Now I can use this, let's call it equation A in the first equation. So use A in first equation. So what will happen is that we will replace I1 with this equation number A. So this equation I'm talking about will become 16 times 3 by 2 I2 minus 12 I2 is equal to 12. Now 2 1s, 2 8s. So 8 times 3 becomes 24. Let's do it over here. This becomes 24 I2 minus 12 I2 is equal to 12. And this becomes 12 I2 is equal to 12, and I2 becomes 1 ampere. Okay, now I have I2 is equal to 1 ampere. I can find I1 as well, because I will simply substitute this value in the equation number A. So I1 becomes 3 by 2 times 1 ampere, so implies I1 is equal to 1.5 ampere, right? Now, what is the load current for this first condition? So load current is across this one. We are assuming R3 as a load. So the load current is actually the subtraction of I1 minus I2, because we already discussed this, that I1 is entering from the top, I2 is entering from the bottom, if we follow these clockwise flow of current. So I load 1, and this is for the first case. So let's define it like this. I load in the first case is equal to I1 minus I2. So it implies that I load 1 is equal to 1.5 minus 1. So this becomes 0.5 ampere. Okay, so this is not the last answer. This is actually the answer for the first case. Now we will do the same process for the second case, and we will obtain load current for the second case. And after that, superposition theorem says that simply add the currents and you will get the final result. So in the second case, what we will do is that we will use this voltage source V2 and short circuit V1. So let's do that. We will solve the circuit for the second case and keep V2 as active. V2 is active, which was 6 volts, and V1 was 12 volts. So now we will short circuit this first source and keep other components as it is. This was 4 ohm, if I remember correctly. This was 6 ohm, and this was 12 ohm. Now we will follow the same process we did for the previous case, but now this second voltage source, which is V2, this is active, and the first one becomes inactive. And since this is voltage source, so we will short circuit it. You will later on see in the second example that when we will use the current source, so that will actually be open circuited, not short circuited. Okay, so voltage sources are always replaced with short circuit. Current sources are always replaced with open circuit. So let's begin with the KVL in each loop. So this is the first loop. So let's apply KVL in the first loop. Since this is short circuit, so it will actually have no influence now. This will be 0 volt. So we can directly go to this one. Voltage across R1 plus voltage across R3 is equal to 0. Now voltage across R1 is actually I1 R1 plus voltage across R3 is actually I1 minus I2 times R3 equal to 0. Now you must understand this by now, right? Because I1 is the current loop current. So this should appear first, minus the second loop one, right? When we will apply the KVL in the second loop, then the current in that loop will be I2. So this equation will become I2 minus I1. So since we are doing this for the first loop, so this is I1 minus I2 times R3, right? And this should be equal to 0 because of KVL. Now simply substitute the values. So R1 is 4 ohm, so this becomes 4 I1 plus I1 minus I2 times R3 plus 12 ohm, so this becomes 12 equal to 0. So this becomes 4 I1 plus 12 I1 minus 12 I2 equal to 0, and this becomes 16 I1 minus 12 I2 equal to 0. So this is our equation for the first loop when second voltage source was active. So let's call this as equation number 3. Now we will apply the KVL in the second loop. So let's do that in the next slide. Now applying the KVL in the second loop. So this is actually really easy. We will start from here, right? So this becomes minus V2 plus voltage across R2 plus voltage across R3 equal to 0. So V2 was 6 volts. So I will simply replace it with 6 plus VR2. So this becomes I2 R2, right? For the voltage across this resistance and then voltage across this resistance. But remember, since we are applying KVL in the second loop, so the currents will be subtraction of I2 minus I1. So I2 minus I1 times R3 equal to 0. Now I will simply substitute the values. So this will become minus 6 plus R2. This was 6, right? This was 6. So this becomes 6 I2 plus I2 minus I1. And R3 was 12 equal to 0. So this becomes 6 I2 plus 12 I2 minus 12 I1 is equal to 6. And rearranging this equation, so this becomes minus 12 I1 plus 18 I2 equal to 6. So now once again we have two equations, two unknowns. So we will simply use linear algebra, or you can use calculator or any other programming tool to solve this equation. So let's do it using linear algebra and solve and find the value of I1 and I2 for this second case. So let's rewrite the equations. So we got this equation minus 16 I1, 12 I2 equal to 0. This was the third equation. And our fourth equation was minus 12 I1 plus 18 I2 equal to 6. So I told you, use the equation which has 0 on the right-hand side for solving it using linear algebra. So once again, using equation number 3, we can derive I1 like this. 16 I1 is equal to 12 I2, or I1 is equal to 12 by 16 I2, or we can say this becomes, if we divide it by 4, this becomes 3 by 4 I2, right? This is the value, or this is the function of actually I1 with respect to I2. Now I will simply substitute this in the next equation, which is the fourth one. So this becomes minus 12. I1 is 3 by 4 I2, right? Plus 18 I2 is equal to 6. So 4 times 1, and this becomes 3. And this becomes 3 times 3 is 9. So this becomes 9 minus 9 I2 plus 18 I2 equal to 6. So this becomes 9 I2 equal to 6. Let's solve it over here. I2 becomes 6 by 9, which is 2 by 3. So the value of I2 is actually 0.667 ampere, right? Now I can derive I1 because I have this equation over here. So I1 is equal to 3 by 4 times I2. Let me use the fraction. So that is 2 by 3. 3 cancels out with 3, 1 time, 2 time. So I1 becomes 1 by 2, which is equal to 0.5 ampere. Now, the load current using the second voltage source, because that is the concept of superposition theorem. First, you have to solve the circuit for one source. Once that is done, then you have to solve it using the second source. So we previously calculated IL1, right? Now we need IL2. So this is actually I1 minus I2. So this becomes 0.5 minus 0.667 ampere. So IL2 actually becomes, let me use the green pen. IL2 becomes minus 0.167 ampere, right? So now we have current across this resistance using the first source, which was IL1, right? And now I have calculated the current across this resistance using the second source. So according to superposition theorem, I simply have to add these to get the final result. So let me do it right here at the top. So total load current actually becomes load current due to the first source plus load current due to the second source. So previously we calculated these values. So previously we calculated this as 0.5, right? You can see in the previous slides, this was 0.5. And now we have calculated IL2 as minus. So this should be addition and minus is the value. So we don't care about that. Minus 0.167 ampere. So IL becomes 0.33 ampere. So this is the final answer. Load current across this resistance. Okay. Now we have a current across this resistance, so we can multiply it with R3 to find WL as well. WL is actually load current times resistance, right? So actually this is the answer. We were trying to find the load current across this R3 and we got it over here. In this example, we assumed two voltage sources. In the next example, what we will do is that we will assume one voltage source and one current source and see how our result changes and how our approach will change. Because when we replace this with the open circuit, then this will be open circuit and there will be no flow in the right hand side. So our results will definitely change. Now we will solve a second example. In second example, what we will assume is that we have one voltage source, right, and one current source. So previously, this is the same circuit from the previous example, but now we have one voltage source, and I will replace this second source with the current source. And for current source, you must remember the direction is like this with an arrow inside the circle. Okay, so whenever you see a circle and there is an arrow inside that, so you should know that this is the current source, and all the values actually remain the same. This is 4 ohm, this is 6 ohm, and this is 12 ohm, right? R3 is actually the load resistance. So we will follow the same concepts which we studied in the previous example, but the only thing that will change now is that when we consider the first source, which is voltage, then for the second source, which is current source, this will become open circuit. So let me redraw it over here. For the first case, so when we will be assuming the first case, we will have the voltage source as it is, and then resistances, they will stay same as before. For the current source, remember, in superposition theorem, this becomes open circuit. Voltage sources become short circuit and current sources become open circuits. And everything will remain same as before. Nothing else will be changed, only the source will change. So this is for the case A. In case A, we use the first voltage source, right? Now everything stays the same as before. We will simply apply the Kirchhoff's voltage law. So Kirchhoff's voltage law actually tells us that the voltage in the loop, the sum of the voltage in the loop is always 0. Okay, so let's proceed with this. So when we draw this diagram, so first step is to define the flow of current. So we will assume that the current is flowing in clockwise direction. So this is I1, this is I2. We can already see that in the right hand side loop, there is an open circuit. So it means that I2 is 0. So that is a good news for us because that means we don't need to apply KVL in the second loop. We need only one KVL, that is in the first loop. But during that scenario, we must understand that I2 is 0 because of the open loop. So even at the beginning, I have already found out the value of I2. Previously, if you remember, I was solving the equations using linear algebra and tried to find I1 and I2. But here in the beginning, I already know that I2 is 0 for the first case. Now to find I1, let's apply Kirchhoff's voltage law in the first loop. So this will become minus V1 plus voltage across R1 plus voltage across R3 equal to 0. So V1 is 12 volts. So 12 plus I1 R1. Now recall the concept. We are applying Kirchhoff's voltage law in the first loop. So this will be I1 minus I2 times R3 equal to 0. You can directly write it as I1 times R3 because I2 is 0. But I suggest you to write it like this so you can have a better practice for circuits with 3 meshes or 4 meshes. Okay. So let's go with this approach, which is a standard approach. So I1 minus I2. Now I will substitute I2 equal to 0 because I already know that and I have the values of resistances. So this becomes minus 12 plus R1. This is 4 ohm. So this becomes 4I1 plus I1 minus this is 0. So R3 is the value of R3 is 12. So this becomes 12 equal to 0. So if you look here, I have one equation and one unknown. So this becomes 16I1 equal to 12 and I1 becomes 12 by 16. So I will get the value as I can divide this by 3 by 4. So this becomes 3 by 4. So implies that I1 is equal to 0.75 ampere. Right? So I've calculated I1 and I2 I already know. So I don't need to apply KVL in this side. So the first case is already finished, right? Now the thing is I have to find the current across this one, right? So the current across this one is actually really simple. That will be 0.75. Why? Because let's apply the formula for that. We studied this previously. I load 1 is equal to I1 minus I2. Since I2 is already 0, so IL1 becomes 0.75 minus 0 and IL1 is equal to 0.75, right? So for the first source, we have already calculated the load current, also I1 and I2. I2 was very simple because when we draw this circuit diagram with open circuit, we already know that there will be no flow of current, so that means I2 is 0. Now what we will do is that we will solve the circuit for the second source, and deal with the first source as a short circuit or open circuit. So let's do that in the next slide. So for the second case, we will use this current source, right? This is current source. I'm using the previous diagram, so I have to update it again and again. So this is the current source. Now the diagram will be updated because we are dealing with the second source and the first source will be inactive. So when this becomes inactive, since this is voltage source, so this will become short circuit. So let me draw this. This will be a short circuit between 2 points, right? This is V1, which will be 0 volts because of the short circuit. This is R1, then we will have R3. So we will connect them, and then we have R2 and a voltage, current source over here. This stays as this, and IS is actually 2 ampere given to us. R2 is 6 ohm. This is 4 ohm. This is 12 ohm. Now, once again, we have to do is to define the flow of current. So let's go with clockwise direction. So this will be I1, this will be I2. Now, once again, we know that in this circuit, the flow of current is IS due to the source current, right? So I2, we can call I2 as 2 ampere because we already know that. So we don't need to apply KVL in this mesh. So we can directly call this I2 as, sorry, to use a red pen to be consistent. So I2 is 2 ampere. We already know this. Actually, what happens is that with current sources, the problem becomes much more simple. With voltage sources, we have to do a lot of mathematics, but due to current sources, we already know the value of currents uh, in each mesh or loop. So we don't need to apply KVL. Similarly, for this case, if we look over here, for this right-hand side loop, we know that source current is 2 ampere. So in series, we know that the current stays the same. So we will have I2 equal to 2 ampere. Now simply we have to apply Kirchhoff's voltage law in this left-hand side loop. So let's do that. So this is actually really easy. That will be, now V1 is 0, so we don't need to write anything for that because that is short circuited. So we will have VR1, which is the first resistance voltage, plus VR3 equal to 0. So VR1 is actually I1 R1. Now VR3, once again, R3 is shared between both loops. So since we are applying KVL in this circuit, so this will be I1 minus I2. I1 minus I2 times R3 equal to 0. So the value of R1 is 4. So this becomes 4I1 plus I1 minus I2. R3 is 12, right? This becomes this equation. So this becomes 4I1 plus 12I1 minus 12I2 equal to 0. So this becomes 16I1 minus 12I2 equal to 0. For I2, I know the value is 2 ampere. So I can substitute that over here. So this becomes, let me do it over here, 16I1 minus 12. I2 value is 2, right? This is equal to 0. So 16I1 minus 24 equal to 0. I1 is equal to 24 by 16, right? And this becomes, if we divide it by 8, 3 by 2. So I1 becomes 1.5 ampere, right? Now the load resistance will actually be different because at this time we don't have I2 as 0. Previously it was 0. So now the load current, okay, not load resistance, load current will be I1 minus I2. So I1 is 1.5 ampere minus I2 is 2 amperes, right? These are units. So IL2 is equal to 0.5 with negative sign, right? Now, if we apply the superposition theorem, so superposition theorem says that finally you have to add all the currents together to get the final result for the load current. So let me do it here at the top. So IL is equal to IL1 plus IL2. So IL1, this value was actually, I don't remember what was this value. I need to go back. But this one is plus minus 0.5. And when you solve this, you will get the result for the IL. Let me see what was the value of IL1. So IL1 actually previously was 0.75. Actually, I don't know how this PowerPoint software works. I am unable to edit the previous slide. So this was IL1 and IL2 we calculated as minus 0.5 ampere. So finally, according to superposition theorem, the combined load current will be the addition of these two across this point, which is actually RL. And this is actually for the second numerical problem where we are assuming one voltage source and one current source. Okay, just remember that. So IL becomes 0.7 plus minus 0.5. So finally, load current for the second numerical problem is 1.25 ampere. This is the final answer. Just remember that there are two cases. So the first case is A, in which V1 is active and the second source is inactive. Okay, since the second source is current source and then this will be inactive, it means we have to open circuit this. Then we will apply KVL and solve all these mathematical equations. But since this will be open circuit, so for the first case, this actually becomes really easy. The I2 current will be 0, and we only need to apply KVL in the first loop. Then for the second case, we will have V1 as inactive, and IS will be active, right? So if V1 is inactive, since this is voltage source, so this will be short circuited, which means V1 equal to 0. Or simply you can short circuit this and omit this component from the circuit. Once again, this will be really easy to solve because in the second case, IS is active and we already know the value of IS, which is 2 ampere given to us over here, right? So we don't need to apply the KVL in the right hand side loop. We will only apply KVL in the left hand side loop and we will derive the values of I1 and I2. For each case, we will derive I load 1 and I load 2. So I load 1 is actually the subtraction of both currents. Same goes for this one. The reason is if we look at this loop, so I1 is actually entering from the top, right? If we follow the clockwise convention, and I2 is entering from the bottom. So this would be the subtraction. You may have a case in which you will have like a circuit in like this, right? So you may have a situation in which you will have one one resistor shared in multiple meshes. So this equation will change differently. So you only have to look at the direction of the currents in that component. Since it is opposite in this example, so this will be subtracted. Once we find IL1 and IL2, we found this for case A, this was for case B. Then according to superposition theorem, we simply have to add them and get the final result. And we got this value for the load current. Once again, if we want to find load voltage, this will be VL times RL, which is IL times R3, right? So this was the second example. Next example, what we will do is we will use a circuit with two current sources. Oh.